Hey everybody, today this video I'm going to be talking about vapor-liquid equilibrium graphs. So my objectives for today are to give a little quick summary of Vienna and Mellon. Then I'm going to be getting into phase diagrams. Then I'm going to get into azeotropes, and then lastly I'm going to finish off with understanding graphs visually and understanding graphs also with a ruler, which is going to be super important when dealing with word problems on this kind of stuff. So to start, like I promised, I'm going to talk about Vn and Ln. So here I've written the two equations you're going to need for Vn and Ln. I'm going to label as 1 and 2. So Vn describes how much of a system is in the vapor phase, is in the vapor phase. And then Ln, as you can guess from the L, describes how much of a system is in the liquid phase. The liquid phase. And to show this visually, I'm going to draw a little jar here. And in this jar, let's say I have some water and I have some methanol. Okay? Oops. So I have them in vapor-liquid equilibrium, and let's say this squiggly blue line denotes the part that's in liquid. So in this jar, you're gonna have water particles everywhere. They're gonna be flying around in the liquid and the vapor, and the same thing with methanol. It's gonna fill this jar, and you're gonna have methanol a little bit everywhere. So Vn or Ln. They don't describe methanol in particular or water in particular. They just describe how much of this system is totally vapor and how much of it is totally liquid. So looking at what you can see from my jar, maybe this might be, I don't know, 0.3 for my Ln, for the part that's in the liquid. And the parts in the vapor, that's maybe about 0.7. Okay? So yeah, Vn and Ln, the maximum is 1, and obviously the minimum is 0. So if I have a jar with none of this squiggly blue line here, and it's just all my methanol and ethanol, well, obviously you're going to say that, okay, Vn is equal to 1 and Ln is 0. There's no liquid, okay? So it doesn't describe how much water or is in the system. It just describes how much of the total system is in vapor or liquid phase. All right, now getting into phase diagrams. So there's two types of phase diagrams you are going to see. The first one is going to be a temperature versus x1. This could be y1 or z1. A verse mole fraction diagram. Okay, this is number 1. The second one you're going to see is a pressure versus mole fraction. So again, that could be like x1, y1, or z1. Could have easily have been x2, y2, z2. It doesn't matter. Also note, you guys are going to be looking at binary mixture. So you're going to have two species. So it's if it's not x1, y1, z1, it's x2, y2, z2. Okay? Whichever you prefer. So the first one, here, maybe I'm going to draw kind of what you might see as a graph here. Let's say this is like some water and methanol mixture. I don't know, whatever you want it to be. Something like this. You have a graph like this. Let me actually extend this a bit more all the way to the end of my graph. So these phase diagrams on my x-axis, where my mole fractions are, these are only going from 0 to 1, hence fraction. 0 to 1. Okay? Also, you're going to have to know if I have a T versus mole fraction diagram, that means throughout this process, the pressure is constant, okay? And the same thing for number 2. If I have P versus mole fraction diagram, that means my T is constant throughout this, okay? Now, when I look at these graphs, I see two curves. Well, I see a line and I see a curve. When I look in between them right here, this whole area right here, and this whole area right here, I'm looking at two faces, okay? So anything here colored in green, this is all green. Let's say this is all green in between the two curves. This whole part, there is a mixture of liquid and vapor. So I'm going to have, let's say, methanol and water. I'm going to have methanol and water in the liquid and in the vapor phase at that point. Okay? Now, for graph number 1, outside of that, right here in this area, that's all vapor. And then below it, in this point here, this is all liquid. Okay, here maybe I'll just fix this. So this is number 1, this is 1, and then this one goes like this. Okay? Sorry about the drawings. It should be nicer. Okay, so then for graph number 2, or diagram number 2, whatever you want to call it, here this is going to be liquid, and this is going to be vapor. So that's really important to know where the liquid and vapor parts are depending on if I have a T diagram or a P versus mole fraction diagram. Okay, that's super, super important. Now, something else that's really important is that if I'm looking at one of these diagrams, and let's say I'm over here, okay? I'm on diagram number 1, and I'm just some water and methanol having a good time in the vapor phase. And if we decrease the temperature, if I start decreasing the temperature, okay, for this particular Z1, okay, so let's say water, I'm going to take that as my species 1, and the Z1 is 0.7, okay? So if I decrease the temperature, once I hit this line right here, we call that the dew point, okay? So what is the dew point, you may ask? Well, it is the point where first drop of liquid occurs. So as soon as I hit that line, I've gotten my first drop of liquid, and now I'm going to keep having liquid and vapor mixed together as I go through my green part here. Okay? I'm going to keep having this mixture all throughout this green. I'm going to have liquid and vapor mixing together as I reduce the temperature, and then I go right here and I hit the liquid line, okay? So I've actually hit the bubble point. This is what we call the bubble point. Bubble point, all right, bub point. So the bubble point is the point where the first drop of vapor occurs. Point where first drop of vapor occurs. Or the way we went, the point where the last drop of vapor occurred. Because after that point, as we move all the way, as we move all the way down, we're completely in the liquid phase. Okay? And then the same thing goes for my diagram number 2. Okay? So for diagram number 2, if I'm coming from the liquid and I'm making my way down here, once I hit this line, this is my bubble point. Because I start getting a mixture of vapor and liquid at that point. So it's no longer completely liquid. So I should probably note here at this, all throughout this area where I'm outside on my bubble point, my ln is equal to 1. Okay, I'm completely in the liquid phase. And the same thing here. my Vn is equal to 1. I'm completely in the vapor phase. My mixture is completely vapor. And then, for example, if I go up, I'm going this way. This is when I hit this curve right here, I get my first drop of liquid, because then anything above that up to my bubble point is a mixture of liquid and vapor. So we call this our dew point, first drop of liquid. Pretty straightforward. Just a little intro to show you where bubble and dew points are. All right, azeotropes. So what is an azeotrope? Well, this is where we have a change in volatility. So change in volatility. So you might ask, well, what the heck does this look like on a phase diagram? So let's say I have a temperature versus mole fraction diagram over here. And note again that pressure is constant while this is happening. My graph might look something like this. Okay? So an azeotrope means that I have a binary mixture, let's say, and one of them is more volatile. So let's say I have water and methanol, and at one point water is more enriched in the vapor than methanol is, so it's more volatile. And then at that one point during this, the volatility changes. So that means it's going to be less volatile at one point, and the other component will be more volatile. So the way you can pinpoint where this happens, where an azeotrope happens, is when you see curves intersect. So that would be a point like this, what I've circled in red. So let's say, I don't know, in this specific case, number 1 is going to be water, and number 2 is formic acid. I don't know, whatever you want it to be. So where is water more volatile and where is formic acid more volatile, or is it the same throughout the whole thing? So we're going to start with the left side of the graph up to the azeotropic point, and then we're going to look at the right side of the graph. So for the left side of the graph, remember, this is all vapor and liquid. And let's say I tell you, I don't know, Z1, so how much of the whole mixture is of water, the mole fraction of water in the mixture. Let's say that is, I don't know, 0.3, okay? So I'm going to make my way up, and I say, okay, I'm going to stop here, and now I'm going to draw a constant temperature line throughout my diagram, okay? So I've drawn my constant temperature line, and also we should probably note that this is the vapor and this is the liquid. So I'm going to say for this temperature, I want to know what the x1 and y1 are. So if I want to know the x1, y1 for this temperature, well, I'm only going to move horizontally along this line. So this here is my x1 on the going towards the liquid. And then going this way, this is my y1. I'm on the vapor line, okay? So what do you notice about x1 and y1? If I continue these lines downwards, as I'm showing you now, you know that the y1 is going to be smaller than x1, okay? This might be like 0.1, I don't know, this might be like 0.5. So that means water is less enriched in the vapor phase, okay? So it's less volatile. for this half of the graph. It's smaller than x1. So let's say this is part 1, and this is part 2. Part 1. So water less enriched in vapor. Or another way to say it is y water is less than x water. Okay? Then if I look at point 2, well, here is going to be my x1, and then here is going to be my y1. And if I extend these lines downward, the same thing is going to happen again, okay? Actually, that z is equal to 0.3 doesn't matter at all. I'm just looking at a constant temperature line. So forget I even said that, actually. So if I make my way down, you can see that my x1 is smaller than my y1. Do you agree? Yes, you do. So that means y1 is higher. So at this specific half of the graph, water is more enriched in the vapor phase. It has a higher y than its x. Okay, its mole fraction in the vapor is higher than its mole fraction in the liquid, so it's more volatile. Okay, so that is the key. So number 2, water more volatile than formic acid. Alright, next I'm going to give you a graph, and I'm going to ask you to well, not going to ask you, but I'm going to go through kind of labeling and explaining different points on the graph that I draw. So let's say I give you a temperature versus mole fraction graph. So this could be x1, y1, z1. And my graph looks something like this. Okay. And I say that I have a temperature change, I don't know, say this is like 60 degrees Celsius, and this here is, I don't know, 40 degrees Celsius, okay? So T, we're going to say it goes from 60 degrees Celsius until 40, and it drops, okay? So I want you to describe everything that happens between that change in temperature with that particular Z. So first thing, let's find Z is equal to 0.5. Oops. 0.5. So I'm going to draw a line all the way up, okay, just to make it really, really clear that this is where I'm looking. Okay, now I'm going to be looking, I'm going to start at 60 degrees and I'm going to make my way to 40 degrees. So on this temperature diagram, where is the vapor and where is the liquid? Here is my vapor phase and here is my liquid phase. So when I'm at 60 degrees, maybe I'll do this. I'll kind of label where I'm looking. So number 1, when I'm at 60 degrees, well, I'm all vapor. So what does that tell me? It tells me that my whole system is in the vapor phase. So Vn is equal to 1, and therefore Ln must be equal to 0. Also, since I'm all in the vapor, it means that Yi is going to be equal to Zi. Okay? which is equal to 0.5. Okay? So in the vapor phase, half of my system is going to be, or species 1 is going to be 0.5, and species 2 will also be 0.5 in the vapor phase. Alright, now I make my way down. I'm moving down, I'm moving down. And I get to the dew point, which is right here. Okay? Oops. Keep doing that. I get to the dew point, which is right there. At that point, I get my first drop of liquid, because then everything in between those two curves is a mixture of liquid and vapor. So, let's write 2. This is also true. So this is also true for 2. Then I make my way again, down again, and I'm in between the curves. So now I'm in this area right here, where this green is, okay? So obviously I'm not going to have as much vapor, so maybe I'll write 0.3, 0.3. So my y1, oops, my y1 is decreasing. And x1 is increasing. And because you could see that I'm moving my way towards the liquid phase as we go there. No, that is not true. That is not true. That is a big, big, big mistake by me. So as we're in between these two curves, it's Vn, which is decreasing, and Ln, which is increasing, okay? Because I make my way towards the liquid. The way you actually read your x1, y1 is you look at a constant temperature line. So you might look at a temperature, I don't know, let's say this is like 50 degrees, and you're going to say, okay, here for 50 degrees, this is my y1, and for 50 degrees here, this is my x1. Okay, that's how you read your mole fractions. So yeah, forget what I said before, because that's not necessarily true. Alright, then as I make my way down again, I'm going to hit the bubble point, which is going to be right here. And then I'm going to be all in the liquid phase, so that will be 0.4. So once I hit 0.4, we know that Ln is equal to 1. The whole system is in the liquid phase. And therefore, Vn is equal to 0. Yeah, so that's pretty straightforward. Now, how to use a ruler to solve one of these graphs if you're having to deal with it in a problem. So the way you're going to do it is as follows. So let's say I have a pressure versus mole fraction graph, okay? I'll write mole fraction here. And it looks something like this. Okay, oops. Here's 1, here's 0. And I need to, well, the only time you're going to be using a ruler to solve one of these graphs is to find your Vn or your Ln. So just a little reminder here. Vn is equal to Z1 minus X1 over Y1 minus X1. Or it could be Zi minus Xi. Doesn't really matter. Same thing for Ln. Minus Z1 over Y1 minus X1. And let's say here mole fraction of 1, species 1. So the way you're going to do it is you're going to, like I said, you're going to have a constant pressure line or temperature depending on what kind of graph you're looking at. So let's say we're looking at this specific pressure right here, okay, for this particular Z. So let's say Z is equal to 0.5. Okay. So you can see that Vn and Ln are a ratio. And what's the ratio? Well, let's look at Vn first. For Vn, the ratio is Z1 minus X1. Okay? Now, this is V, and this is liquid on my graph. Z1 minus X1. Well, that's the mole fraction of species 1 in the liquid phase. So here I'm going to kind of circle this part. And here's Z1. So this is the difference between Z1 and X1. So with my ruler, I'm going to measure that. So let's say I measure that, and that equals, here, I'll also write here, this is where I'm going to find X1, and this is where I'm going to find Y1. Let's say that measures 5 centimeters. Okay, so let's say I measure, 5 centimeters. Now I need Y1 minus X1. Okay, so I'm going to take my handy dandy ruler and I'm going to measure from X1 to Y1. What is the difference? So I'm going to measure this length right here. And I don't know, let's say I get 15 centimeters. The centimeters will cancel out and I'll get 1/3, so 33. 0.33 is equal to Vn. Pretty straightforward. Same thing goes for ln. So if I'm looking at my graph, I'll put this part in green now. The numerator is y1 minus z1. So what's the difference in length between z1 and y1? So that would be this portion right here. So I'm going to measure that. And again, I don't know, maybe I'll measure 5 or 7 centimeters. And then, so I fill that in. Same idea. And then I look for y1 minus x1. So again, that's like what I did in red here. I'm measuring that part. And let's say that's 10 centimeters. Then 0.7 or 70% of my system is in the liquid phase.